So there are three things I want us to accomplish today. First of all, I want to talk a bit about the formula sheet that you'll be provided. I recommend you make a hard copy of it. If a hard copy is not possible, in other words, you don't have a printer that's at home or that you can get to, let me know. I will print them and send them to you because I want you to have it hard copy. But let me just kind of walk you through what the formula sheet that they're going to use this year. It's different than what we've been using in terms of its format. The actual sheet itself, the formulas are the same, but the format is a little bit different. So I want to share that so everybody can get comfortable with what they're going to see. So that formula sheet looks like this. And really, I'm just kind of walk you through and talk to you about what we've covered and what we haven't. So the first part is descriptive statistics. We've talked about calculating mean and standard deviation already. These next four formulas deal with regression analysis, which we will cover early next week. That's the one topic that we have not talked about yet. I skipped it this year and held it to the end because it's pretty straightforward, and I think you'll pick it up really quickly. So we'll cover regression analysis early next week. Probability, we've talked about probability and conditional probability. We've talked about discrete random variables, binomial random variables, and if you'll remember, here are the formulas. They also have geometric distributions on here, which is similar to binomial, but I don't think it's very likely that you'll be given a geometric distribution question. Typically, what I've seen is that if there is a test with this on it, it's usually one multiple choice question. I can't imagine that they're going to use the precious question time they have on geometric distributions when it's so similar to binomial. And if you go back in our textbook, there's a half a chapter devoted to geometric distributions. And I think there's a note in there that says it's not typically tested, and so we can skip it. And I have always skipped it. And none of my students have ever come back and said, man, I wish we would have talked about geometric distributions. But if you want to read that half chapter between now and test date, the difference between the two is really straightforward. And maybe we'll take a class period and talk about them just to be complete. But I don't think you're likely to be tested. And if you do have a question, the formulas are right here. I'm certain you can sort it out. And then the third part is sampling and inference. And we have talked about this test statistic, z-score. And we're going to talk about it today and tomorrow. I think by the time we're done tomorrow, you guys should be very familiar with that. Confidence intervals, we've gone through there. The one thing I need to remind everybody, when you're building a confidence interval and it involves a population mean, the critical value comes from table B, where you have to determine the degrees of freedom and go from there. Don't use table A to calculate that critical value if you have a population mean. Use table B. Chi-squared, I've been told through the teacher forum that chi-squared is not tested this year. It's at the end of the textbook. And they told us that particular topic's not covered, so I wouldn't sweat that. And then what you see here are the formulas for inference for a population proportion. These we've talked about, these formulas we've talked about. What you see down here looks pretty nasty. And really, all it is it takes into account comparing two different populations with different p-hats. There's no way you're going to be asked to calculate these values, the standard deviations, because the calculator you're supposed to use is for function. And so I don't think there's any way you're going to have to calculate that. And I don't think you'll be tested over this. We might do an example problem just to give you guys an idea as to how to walk through these if you see it, but I think it's really, really unlikely. And then there's the distribution for inference for sample means, and we've talked about this row here. Here's the difference between two populations. Again, I think it's unlikely that you'll see that. And then sampling inference for a linear regression. Again, this is a unit that I've been told is not tested this year, so I'm not even gonna worry about that for you. That's the formula sheet. Definitely have that printed out and available. If you need it, let me know. I will print it out and send it to you. Table table A, table B, the T distribution for inference about a sample mean. Here's the degrees of freedom. We've looked at this. We'll probably do another example. Well, we will do tomorrow when we look at significance testing for sample mean. We'll look at this one more time. And then table C is chi-squared. I don't foresee you needing that one. So there's there's the formula, the formula sheet. And I think it's pretty straightforward. There's nothing on there except for this yet that we haven't at all seen, and we'll cover that early next week, and then you'll be ready to go. Yesterday we did an example of conducting a significance test for a sample proportion. We did a one-tailed test in class, and then I asked you to look at an example problem from the textbook about parking. And I know many of you probably haven't finished that yet. I do want to show it to you and just kind of point you through the steps. And if you haven't done this yet, then you might just, I don't know, don't close your eyes, but don't pay a lot of attention. There's importance. It's really valuable for you to physically go through these steps. Okay, so the first part of doing any sort of significance testing is to state your null and alternate hypothesis, define what your population parameter is. And then the second part is to check the conditions of inference, which are always the same. Did it come from random data? Is the distribution normally shaped? And are the data independent? In other words, is the 10% condition met? And then you'll need to do a little bit of calculations usually. But the main thing, you may or may not have the p-hat given, and in this case it wasn't. We have to calculate it. The main thing, though, is to go to this test statistic to calculate the z-score. And one point I want to make, I see several of you in your homework, you want to make sure when you do a calculation like this one, you want to make sure you use at least 4 significant digits to eliminate possible sources of round-off error. Okay. So for example, when I computed the test statistic, I wrote my answer down to 4 significant digits, although when you look up z-score in table A, it's only to 2 decimal places. So this little guy out here just helps me know what the last decimal place is. But Um, it is important to keep 4 significant digits in all of your calculations if you round it, if you write it down. And so when you calculate the p-value, then you can either do that using table A, like I did here, or you can use the CDF, normal CDF function. Now, another thing I need to point out, when we get to this point of calculating the p-value is always taken from the standard normal curve. And so in this normal CDF, you want to make sure that you identify the mean as 0 and the standard deviation as 1. That comes from the standard normal curve. Don't allow yourself to plug in this p hat or even the population parameter p0 here, because that's not the distribution we're pulling this p-value from. It always comes from the standard normal curve. So looking at table A, that's the right place to look. And so if you take the z-score and go to table A, you're fine. But if you want to use the normal CDF, make sure you plug in 0 for the mean and 1 for the standard deviation. And then when you get your p-value, it turns out that table A and the calculator function give you exactly the same value to 3 decimal places. Since this p-value is greater than the significance level alpha, then we fail to reject the null hypothesis. And I put this in brackets. This is the template for the language you want to use. First of all, you want to comment that you either fail to reject it or that you do reject the null hypothesis. That's the first part. The second part is you want to state your answer in context of the question, and that's what the second sentence is. There's not enough evidence to conclude that student satisfaction has increased. So there are 2 parts to this interpreting a significance level. First is you need to state clearly whether you reject the null hypothesis or you fail to reject it. Never, ever, 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 never, ever, never, ever, never, ever say you accept it or that the null hypothesis is true. You either reject it or you fail to reject it. And then you interpret that in light of the context of the problem. And so that's the better parking solution. If you have not done it, then please go ahead and do it. You have the solution in Classroom now. I forwarded that to you earlier, right before class. And so you have this for you. You can go back and look at that a little bit more on your own time. Okay, and so we'll do the same thing today. We're going to talk about a two-tailed population proportion test, and it's linked to confidence intervals. And I'll have an assignment for you. So tomorrow I'll give you my solution to that, and you'll have it to go through and compare against your own. You're welcome to submit these in Classroom, but remember, I'm not grading them. So it's up to you as to whether you submit it. If you submit it, I'll look at it and I'll give you comments back. Or you can just wait for us to talk about it in class. Either one is fine. So I'm going to switch gears now and talk about doing a two-sided significance test. And again, I sent you these notes earlier today. You may not have had a chance to print them out or look through them. Doesn't matter. We'll go through them step by step. And at the end of this, we'll talk about how a two-sided test and a confidence interval are linked, and in some ways how the confidence interval is perhaps a little bit better or gives you a little bit more information than just the significance test. Okay, so here's our case. CDC website says 50% 50% of high school students have never smoked a cigarette. Whoever that is, wonders if this is true in his large urban high school. And so he does a simple random sample of 150 students, and out of that 150, 90 say they've never smoked a cigarette. And so what should he conclude? And so we'll walk through the significance test here. So in this case, all we want to know is whether 50% of students would say they've never smoked a cigarette. So we're looking at the null hypothesis is the null hypothesis is the proportion is equal to half. The alternate is that it is not equal to half. So it could be that less than 50% say they've never smoked, or more than 50%. It could be either. So we have to evaluate this as a two-tailed scenario, and P is the actual proportions who would say they've never smoked a cigarette. Again, the question here is who would say they've never smoked a cigarette. We're going to assume there's no bias here in terms of the difference between what they say and what they've actually done. And so we'll perform a one sample Z test for the population. We have to check the conditions for inference. He performed a simple random sample, so we know the data is from a random source. We need to check to see if the distribution is normal. And because this is a sample proportion, the test here is that n times p and n times 1 minus p are both greater than 10. And when we check the arithmetic, we determine both of them are greater than 10, so we're safe there. And then independence is where we want to check the 10% condition. And it seems reasonable that 150 students is less than 10% of a large high school. We're not told how many students are in his school. We're just told that it is a large urban high school, and we can imagine a school in Los Angeles or Chicago or New York or Atlanta, Houston, any of those large cities could easily be more than 1,500 students. I mean, our school is not urban at all, and we've got 1,000 students. So it makes sense. So we'll conclude that the conditions for inference are met. And so first thing we need to do, we need to calculate the p-hat from his particular sample, which is 0.6, and we'll calculate the z-score or the test statistic. Again, pay close attention to the values that you plug in here. P-hat is what he calculates. P-naught is the proportion that we use in the null hypothesis. In this case, it's 0.5. So we do the calculation and we come up with a test statistic of 2.45, which again, we know that that's over two times away, 2 standard deviations away from the mean. So that's going to be pretty unlikely, but we need to just go through. And so when we do the calculation, either looking up table A, or using normal CDF, we determine that the probability of being in either portion of this tail is 0.071. Now here's the trick. In a two-tail, I mean, table A is going to give you this right here. It's going to give you this value right here. What you have to remember for a two-tailed test is that we're considering the area in both halves. So we have to take this value and multiply it by 2 in order to get the actual p-value. On a one-sided test, whatever we get in this tail or that tail, that's all we need. But this is a two-sided, so we've got to take this part and that part. Because of symmetry, you only have to do the calculation once. You just have to remember to multiply it by 2. And honestly, that's the most common mistake students make in the heat of the moment. You forget to multiply that thing by 2. And this is where drawing this sketch somewhere in this step, putting this sketch out here, will help you remember to make sure you multiply that by 2. And quite honestly, if you have the sketch and you highlight this area and that area and fail to multiply by 2, I think your reader is going to give you a better score than if you fail to multiply by 2 and did not include the sketch. So it's possible that they would look at that as a minor calculation error and not deduct quite as much as long as you have a proper sketch. So again, from day one, I told you draw a sketch, and here we are right up at test day, and I'm still telling you to draw the sketch. It is so important to do that. So the conclusion, and I got to be honest with you, all of the money in these questions are going to be writing right here. And quite honestly, especially for this year's test, because it's going to be light on calculations, you really can't do this calculation on a 4-function calculator. So I really believe this value is probably going to be given to you if you need it. And all the money is going to be riding on this part of your response, honestly. So since the p-value is less than the significance level of 0.05, we can reject the null hypothesis and conclude in favor of the alternate, that the proportion of students differs from 0.50. And here's the problem with the significance test. All we know at this point is that the proportion of students in his school who say they've never smoked is not 50%. We don't know whether it's above or below that value at that point. Now, we do know that his sample proportion was 0.6, was above 0.5. But it's possible, it is possible from what we have done here, that the true population proportion is below 0.5. We don't know that at this point. And so the confidence interval, if we calculate a confidence interval, then we could know whether it's above or below that. Now, it can't be both, because if the confidence interval contained 0.50, then we would have to conclude that we couldn't reject the null hypothesis. So we know that the confidence interval is entirely above or entirely below, but right now, at this moment, we might suspect it's above, but we can't prove that yet until we do the calculation. So I think that's what we're going to do right now, is we're just going to go ahead and calculate that confidence interval. And remember how we do that. We have to check to make sure that both of the number of successes and failures are at least 10, and we did that already. But we have to do it using in the past, when we did it before, we used p0. In this case, when we conduct the confidence interval, we're going to use p-hat. We're going to use 0.6. So when we conduct that confidence interval, keep in mind that that's based on p-hat. not the population proportion. So, see, then the formula here, p hat shows up everywhere. P naught doesn't show up anywhere. So the formula is our point estimator plus or minus a critical value, which with a population proportion comes from table A. And you probably remember that the 95% confidence for the 95% confidence interval, that critical value is 1.96. You do the calculations here and you get an interval of 0.52 to 0.68, where it's obvious that 0.5 is outside of the confidence interval, which we concluded that already. We just didn't know whether it was above or below, and now we can tell that it is. The confidence interval is to the right, which is what we suspected with a p hat of 0.6, but until we do the calculation, we're never sure. And then again, here's a statement of our interpretation. We are 95% confident that the interval from here to here captures the true proportion of students who say they've never smoked. Again, we don't know that it could be as low as 0.52. It could be as high as 0.68. So the confidence interval helps us in this case in terms of helping us know whether the true proportion lies above or below our null hypothesis. And here is just kind of a graphic that helps you interpret how these two things are related. Okay, and this one is in general terms. This one does not. This is not talking about Taeyeon's survey here. It is in general for a 95% confidence interval or a 5% significance level. So at the 5% significance level, the area in each tail is 2.5%. And so the mean, it has to be 0.5. We do the calculation, the standard deviation is going to be 0.041. And so if our sample was here, in other words, the p hat that we calculated was here, and we constructed the confidence interval, then p hat falls inside this inside the middle range of the curve, and so we would fail to reject the null hypothesis, whatever it was. If, however, we did a sample and our p hat fell here, where p hat is in the shaded region on one side or the other, you can see that the tail here does not stretch over far enough to get the mean value, the mean of p hat. So we would say it's not in the confidence interval, and we would reject the null hypothesis in this case. Okay, and so I think that's what this little tab here says. And so the real value of the confidence interval, of taking that extra step of calculating the confidence interval, allows you to understand, because the case for analyzing a two-tailed test is the null hypothesis is equal to some p value or some proportion, and the alternate is that it's just not equal to it. Okay, that's a two-tailed test. That's the definition of a two-tailed test, is that it's not equal to it. So we have to make sure that we consider whether that option or that alternative is less than our population parameter, or it could be greater than. So the confidence interval in this case really helps us sort out where our population values lie. Do they lie above our null hypothesis associated with p naught, or do they lie below? And I think I've got, yeah, just a summary. This summary is in your textbook. I'm not going to go through here. It just talks about everything we've covered. But this is verbatim at the end of section 9.1 in the textbook, so I'm not going to cover that. What I want us to do while we're talking about it, I guess I can stop sharing the screen now and get back to face. What I want you to work on to practice this two-tailed test starts on page 563. It's question 49 and 51. Question 49 is about just conducting the two-tailed test. Question 51 has you go and do the confidence interval and compare it with the results from your two-tailed test. So those two things go together. Calculating the confidence interval isn't that much more intensive than what you would have to do anyway. So 49 and 51, again, I will create this as an assignment in Classroom. It's ungraded. So whether you turn it back into me, that's up to you. I'll be happy to look at it and give you comments. Or you can just wait till tomorrow and I'll post my solution. Okay? Any questions? We good? I know there's a lot of information here, but I mean, I can be highly confident that at least one of the two questions will drag you through a significance test. I mean, this is the golden chalice, the holy grail of this introduction to statistics course, and I just know we're going to be there, so we got to get through it. I want you to see it, and I want you to see it at the end, close to the test, so that it's fresh on your mind. Okay? All righty. Well, if there are no questions, I will log off and